vehicle hurtles toward a concrete barrier, but inches before impact, the anti-collision system automatically locks the brakes to prevent a crash. The technology driving that decision is an ultrasonic sensor, a spatial measurement tool used throughout the automotive industry and in autonomous robotics. Over the next 5 minutes, you are going to wire, write the code, and test your own functional virtual sensor using the Tinkercad simulator. Mastering how to control this single piece of hardware is the first step toward building machines that can navigate safely through real-world spaces. Inside a blank Tinkercad workspace, start by heading to the component search bar, indicated by the red arrow. Accuracy is critical here. Select the 4-pin HCSR04 sensor, not the 3-pin version, and place it in your workspace next to an Arduino Uno. Wire the power first. Route the sensor's VCC pin to the Arduino's 5-volt output using a red wire, and connect the GND pin to ground using a black wire. For the data connections, route the trigger pin to digital pin 9 and the echo pin to digital pin 10. This schematic shows your completed wiring path. While the hardware is now physically connected, it will remain inert until code establishes the rules of communication. Open the Tinkercad code interface, switch the mode from blocks to text, and then clear out the preloaded starter code. First, define pins 9 and 10 in your script. Then, inside the setup function, initialize the serial monitor at a 9600 baud rate. Inside that same setup function, designate the trigger pin as an output, as its role is to drive the sound wave out into the environment. Designate the echo pin as an input, because its only function is to listen for the returning signal. Explicitly defining these roles ensures the Arduino's internal circuitry knows whether to drive a pin with voltage or listen for an incoming signal. Inside the main loop, start by clearing the sensor. Set the trigger pin to low for exactly 2 microseconds. To fire the 40 kHz sonic pulse, set the trigger pin to high for exactly 10 microseconds, then immediately return it to low. Use the pulse-in function on the echo pin to record the total travel time of that sound wave. As you can see in this diagram, the recorded time represents a round trip, from the sensor to the wall and back again. To find the one-way distance, multiply that duration by the speed of sound, 0.034 centimeters per microsecond, then divide it by 2. This calculation isolates the distance between the sensor and the object, turning raw travel time into a usable spatial coordinate. In order to make this calculated distance readable, you need to format the raw variable for the serial monitor. Add a serial.print command to push the numerical distance, add a CM unit label, and include a half-second delay. Structured formatting turns the Arduino from a silent processor into an interactive diagnostic dashboard. Click Start Simulation and open the serial monitor at the bottom of your workspace. Click the virtual sensor to reveal its interactive cone. Drag the object closer, and you will see the distance data update instantly in the monitor. To test your new setup, try expanding your code by adding a buzzer that activates if the object breaches a 50-centimeter threshold. Successfully reading environmental data is the first step toward engineering machines that can independently react to the physical world.